Sorry. Um, let's get started. First, I want to know how many of you transferred in from a community college. All of you? All that many? I put up those hands again. I got to kind of see if I got this right. Okay, I thought I knew you two. I wasn't sure about you. I was pretty sure about you two. And you, wasn't sure about you. I was pretty sure about you. Okay, the reason I'm asking is that uh, I'm a member of a um, there's a group over in sociology that's doing a research grant, and I'm one of their, how do you put this, their advisors, and they asked me if I could help them find a couple of people that transferred here from the community college, and they want to test a uh, survey they've got, but it has to be done. I think they have to ask you the questions, and it's got to be done over Skype. So, some of you may get an email from me asking, feel free to say no. They said the people that I get to do it, they would, or that, they select out of the ones I send to them, uh, they would pay them $25 for it. It wouldn't take too long at all. But, huh? Anyhow, and I know some of the DE students, they're all from a distance ed, and that might work out just great for them. So let me get back to them because uh, some some of the things that they're doing is they're trying to find out what is, and Greg should be all over this, what's keeping women from getting into the STEM programs. He is all over that. He was helping me earlier, and I thought he knew every girl on this campus. So now they know him. The everything. He didn't mind sharing anything. Anyhow, they will. I will give them some names. It could be that they would like to have some females instead of all males. So we'll see what we can do. Yeah, we do. I ran a project on this campus. This is why she says I'm one of their experts for their panel. Is that I ran a project on campus for 7 years to try to increase the diversity of this program. Every time I looked out, this is what I saw. It's like this is ridiculous. I want to see. I'd like to see some girls in here. Okay, let's knock this stuff out. Uh, you guys try to remember to hold it down back there because nobody can hear me if you're talking too loud because I don't talk loud at all. We need to look at all this stuff. Okay, we need to look at structure and entity. This is all VHDL. We're going to look at some combinational circuits. Some of this stuff, the ones that are real important here are the if then else and the case statements. Those are the ones that are going to be used probably the most out in your projects. One of the best things about any HDL is that you don't have to really do the design and say, well, look, I need some JK flip-flops here and some T's here and this much memory and this and that and the other. But what you do is you describe what you want, okay? And and when you describe it, then Xilinx or Verilog or whichever you're using creates a circuit for you. So some of this, and I'm going to be real particular about it, we synthesize these. These are not programs, they're circuit descriptions. Okay, there's a difference, and I'll eventually be able to point out, I'll have a good example where I could really point it out. Okay, and some of them are in this one. Okay, so we got to know this, and we got to go through this as quick as we can so that I can get to explaining some stuff so that you can get on project 4. So I think we're falling a little behind here. We already know this much about the entity and the architecture. The entity describes just the black box, inputs and outputs, and then the architecture describes what's in there and how it works, and either the logic in the design or how that design is going to behave. Now here's one way of doing something. This is a 2-input OR gate. You would never do this with VHDL. Why? You could do this by just hooking up a 2-input OR gate. Okay, so I'm not going to go with all the hands-on stuff today. Here, I'm trying to make sure that you know that all the bolded words, you can tell which ones are bolded. Those are keywords for VHDL. Notice by now we're doing all standard logic. Right now we're not using any signals in here. But this is one way to do a 3-input NAND gate. We AND A, B, and C, and then we put a NOT in front of that. That's just one way to do it. Again, you won't be doing anything like that. This is to go back and get you used to what are these things, like the ports are the signals that go to the outside world. The architecture is the behavior of that. Now this we haven't talked about too much at all. Ports have a name, okay, A, B, or C here. They have a mode, input or output. There's also a couple others. And then a type, and in this case it's standard logic. Now this one, we're using standard logic. It's they can take on 9 different values. I've told you that before. I also told you I couldn't actually remember every one of them. But if you put 0 or 1, it's like you are forcing that logic 0 or forcing that logic 1. It's and it's okay inside the VHDL circuit description. It may not be okay outside in the real world in a real project. High impedance, you'd be using that if you were using an address bus or a data bus or something like that. And this is a don't care, just a dash. And I've never had a weak low or a weak high, so I can't really explain what those mean. Okay, then we've also got, as far as the mode goes, we have an in and out, an in out, or a buffer. Okay, this one, a lot of folks, like I've said, are very they're very tempted to use that when we get into some more complicated stuff, but it's not that we need an in out, it's that we need a signal in here instead of a port value, and we'll get into that again a little bit more later. Okay, this is the different kinds of architectures that you can have: a structure, a behavior, or a data flow. The structure is a lower level, okay, than the other two, and includes instantiation of components like AND gates and OR gates and all that. The behavior type is a higher level, and that's the one I want to get to real soon, because you don't want to have to describe these state machines, you don't want to have to describe them in a structure by doing all the AND gates and stuff like that. You want to be able to just say this is the way that they behave, and then let VHDL come up with it for you. And then the data flow uses some of the conditional selective assignments, but also includes some Boolean expressions, and we're going to see how a lot of that works. Okay, we've used some of the simple operators. We're also going to look at some of the conditional and selected signal assignments. Those allow a signal to be assigned one of several levels based on some kind of criterion, and that's this kind of thing right here. Okay, so when I say selected signal assignments, I'm talking about using this kind of a structure inside the architecture. You're saying with some input, select, and that's the syntax. This should actually be bolded so that we know that there are keywords. So here what we're doing is saying when S is a 0, make F equal to whatever is W0. So this is a 2-input mux. Okay, and I'm assuming here on this 2-input mux, it has WO and W1 connected to the 0 and 1 inputs, 1S for the selector, and F is the output. Okay, so we want whatever's on W0. If it's a 0, if it's a 1, you know, whatever is on that particular input, it should appear at the output when S is 0. And notice that has a single quote. This is going to become real important in just a minute. Then here we say, but it's W1, and that's a comma operator. So it's 0 when, or W0 when 0, W1 when others. Now, why do you think we would say others instead of when it's 1? Because it might be don't care. It's like a default statement. It could be a default statement. It's really basically this. It's like we're saying if it's forcing 0, well, if it's a weak low, we want it to be the other one also. So this is taking care of all of these to make sure, and those other ones that aren't shown here, this is 2, 4, 6. There's 3 others here that I can't remember. But it's trying to make sure, it is kind of like a default to make sure that you capture all those others. Because what would happen if this is, if you said W0 when 0, W1 when 1, and it was a weak low, it wouldn't know what to do, right? It wouldn't be able to assign something here. So that becomes real important to put that others in there like that. Okay. Oh, great. What are they playing over there now? Here, they've got, this is the same one, isn't it? Shouldn't take much more explanation than what I've already given. Okay. And the others there is just saying that every other possible value is there. All right. Here's another one. Now we're starting to get to something else that becomes important. I'm not using single quotes. I'm using double quotes. And we've got the same kind of thing. This is a 4-input mux. So we've got S as a selector, but S is a 2-bit. And I've got 1 down to 0. So is this bit 0 or is this bit 1? So am I saying this is 0, this is 1, and this is 2? Or am I saying this is 0, this is 2, and this is 1?
1 down to 0, so it should be from left to right.
When I'm saying 1 down to 0, I'm saying the one on the left is the most significant bit. Okay, 1 down to the other one. Okay, so here, this is the way a multiplexer works. The S inputs, there are two of them. When they're both 0, we're selecting the first input 0. When we get a 0, 1, it selects the second input. When we get a 1, 0, we're selecting the second input, and or the third input. And when anything else is there, we get the last input, and then those appear on the output. But again, we got to use others. And look here that they're double quotes, not single quotes. That's real important. We're telling it it's like when you put 0, it is the value 0. Here I'm saying a variable s only, but it is a vector, but we have more than one value there, 0, 0. So it's almost like a string, and you've got to put it in there as uh, a string with the two or double quotes. I've seen enough where I've made errors with this, or I put in a single quote or double quote. That was the most often made error, was putting a double quote around a single 0 or a single 1, and it'll give you some errors, and you won't know exactly um, what it is, what it's talking about. Okay, here we're looking at, let's say, what is this? A 2 to 4 decoder, I think is what it is. Does it say in there anywhere? Anyway, we've got something over here. We've done something like this before. We're taking two of the signals. One is this enable signal, okay, EN, it's a 1-bit signal. And then we got W that is a vector 1 down to 0. So this one can be 2 bits. And what we've done is we've decided to concatenate them, make it all into one variable to make it easier to work with. And here's where we make that assignment. We say that this signal ENW is assigned EN concatenated with W. So the first bit will be EN, the second 2 bits will be W. Okay, now I played a trick here. Here's 0 to 3. So that means that that this is bit 0, bit 1, bit 2, bit 3, right, for Y, because I did it backwards. And I did that to emphasize that, not because this is the way I would do it in a normal situation. I did it to emphasize that difference. So we got when we want Y, the output of this decoder, to be 1, 0, 0, 0. So the lowest bit has got to be high when this thing is enabled and we've selected the lowest output. When, let's see, when our enable is 1, you got what? You got a question? No? I thought you went like this.
No.
Okay, all right. I just thought, okay, sorry. I thought there was a question. I must have been hallucinating again. Uh, Once more. It happens all the time. Uh, Someday I'll tell you some of the hallucination stories. Those were good. Uh, those were a lot of fun. Actually, my wife and daughters like to tell them more than I do. I was in the hospital, and it was some strong medicines they were giving me. And anyhow, I saw some interesting things. And, say what? No mushrooms in front of your family. No, there were no mushrooms growing around my bed. Uh, Here, all of these are saying here that when the enable bit is 1. So I haven't said anywhere when the enable bit is 0. But I am giving all the possible inputs to this. It's 0 or 1 or 2 or 3. And this allows our decoder outputs to have a 1 active high when we're selecting the right one. So then if enable is 0, and that's the only possible bit or inputs for 0, 1, 2, and 3 for W. So when the enable is 0, then everything else is off. So uh, so we just say when others there. So everything else would be zeros. And again, you're not, you might be able to do this, but this is not the way we're going to be using VHDL. We're going to be using it in the form where we describe the behavior of a circuit. Okay, here's a conditional. It's another way of doing it, but it's a conditional statement. Should look very similar to the last one, so don't get them confused. And this again is a 2 input mux, and we're saying that F is assigned W0 when S is equal to 0, else it's going F is the way we read that is going to be W1. So it's the when else. Okay, and then over here, this is the same thing. With S, select this. We've already done this one. This is the same thing. It'll give you the exact same circuit. So it's up to you which one you want. Here, this is just a little bit more complicated. We've got Y is equal to 1, 1 when W3 is 1, else 1, 0 when W2. This is a priority encoder. 1, 0 when W2 is 1, or 0, 1 when W1 is 1, else we want to make the output 0. And then Z is the other output here, and we want it 0 when all the inputs are 0, else we'd make it a 1. And that's just the way those things work. Okay, we're not going to do this one. We've done this before. 2 input muxes we've already done enough of. And this is another solution of a 4 input mux. Okay. Okay, now here it's looking a little bit better as a more of a, it's looking more like a behavior. It still isn't quite behavioral, but well, here we're describing a comparator, and we've got an A and a B and their inputs. They're 4-bit inputs, and we've got these possible outputs: A equals B, A is greater than B, or A is less than B. So it's a pretty simple description here. A is equal to B, or A equals B is 1 when A is equal to B, else it's 0. A is greater than B when A is greater than B, else 0, and so on. So that's not a very complicated one at all. Any questions yet? I know I'm flying through these, but most of these to me seem pretty straightforward. Okay, to change this so that there's a 16-bit unsigned comparator, this is an unsigned 4-bit comparator, all we should have to do is change that to a 15. Okay, that's all we have to do. All right. Now, we could also do this. 15, you signed in here. Here was standard logic. This one, it was changing this code above to make it a signed comparator. And here we first have to put in the arith, instead of unsigned. And then down here, we've got to put in signed to make sure. But these are here mainly for your, you can look these up when you need something like this. Okay, we're almost done with this set of slides. I wanted to get them done as quickly as I could. Let's look at the if-then statements in the case. Now, these are the ones that we might use a little bit more. And they're going to use a process statement, and the process statement typically requires a sensitivity list. Okay, and that means because of one of the inputs changing, then we want this process to start or to get activated. And if that doesn't happen, then we just want it to sit there. So this could be a lot like a flip-flop works. That when you know the clock goes from 1 to a 0, then do something to the output of Q. Okay, so let's look at this one. And sometimes these sensitivity lists don't always make sense. Okay, then we're also going to look at the signals inside the process that aren't visible outside, and then some multiple assignments to the same thing. Okay, here we go. This all should look the same. Okay, we're back to a 2-to-1 mux. I keep using the same one not to bore the crap out of you, but so that you could go back and look at these different methods and then hopefully apply them to different things yourself. So this says we are going to have a process. The sensitivity list is all the inputs. So if any one of the inputs change, then it wants us to run this process. And the process says if S is 0, then make the output F assign W0, else assign it to be a W1, and then end that if. And that ends the process. So none of this happens at all until W0, W1, or S changes state. When that happens, it kicks in this process. Okay. We could have done it this way. So here we could have said F is assigned W0. If S is equal to a 1, then F is assigned W1, and then end the if. I tried all these beforehand, and I think they worked as far as syntax. I'm not positive this works as far as I'm not sure that's going to work as far as the actual behavior of a mux, a 2-input mux. And the reason I'm saying that, in a process, all these have to change, or only one of those has to change to begin the process. But one of the weird things that makes this a little bit different from a program is that if we assign F to be W0 and then a little later assign it to be W1, if this was a program, it would make that change immediately. But in this, it won't make that change until the next clock cycle. And we'll get into some better examples than just that. Okay, here's a case statement. It should look a lot like the switch case statement that you would use in C. It's the same kind of thing. We have our case. In this case, the case is S. And it says case S is when it's 0, 0, then X is assigned A. When it's 0, 1, then X is assigned B. When it's 1, 0, X is assigned C. And when it's any others, X is assigned D. And then we end the case. You will be using this more than anything else for your state machines. You'll be using this a lot. So you need to know at least the last few sections or pages of this particular set of slides, because this is going to become important. Okay, here we've got a case statement. Again, we've got a process. It's within a process. So we tell it to begin. One of these have to change in order to kick this process in. And we're hoping that S changes. If S changes, then it's, if it's 0, then F is assigned W0. When others, it's assigned W1. Again, that's a 2-input MUX. It's just another way of doing it. Okay. This was a hand-on. It was to do the same kind of a thing. Write the code for a 4-input decoder or a 2 to 4 decoder using the case statement. Instead of making it a quiz or anything like that, I gave this as an example, and I think I ran the whole thing to make sure it worked. So here is our process. If one of these inputs changed, W or the enable, then we could get the thing going. If the enable was 1, that was the first thing that had to happen. If enable was 1, then we could go in and look at what W was. This is tied with this else that says just make Y all zeros. Okay, and then we end that if. Then our case is from here to here, and the case is on W. When it's 0, 0, we want the output to be 0, 0, 0, 1. That's correct this time because I got 3 down to 0 instead of 0 to 3. And then when it's a 1, we have a 1 on the output. When it's a 2, we have the 4 on the output. And when it's any of the others, we have the 8 on the output. And that's just a possible solution. You may come up with several other different things. Now here's a good possibility for a case statement. If you needed a BCD to 7-segment decoder, have those ever come in, or have you ever had a chance or a case where you needed one of these? Typically you do. You had that in your last lab assignment. We did it a little bit different. We did it with all circuits instead. But here we're saying if the inputs of our BCD to 7-segment, if it's BCD, it can only be from 0 to 9. So I've got having a 4-bit input, saying it's 3 down to 0, that's our BCD input. And our LEDs, I changed that 1 to 7 because the one to the left is A. It is it made more sense in this case for me to do it that way. But the syntax on these is kind of screwy. It's all in a process. We only want to, our sensitivity list is just the input BCD. Then we say begin, and then on that BCD, when it's all 4 zeros, then I want this to be the output on the LEDs that makes it light up. Well, if it's 0, it should light up A, B, C, D, E, F, and then G should be off. So I've got A, B, C, D, E, F are all 1s. I'm assuming that this is a common cathode type of 7-segment LED, and this 0 would turn it off. What does a 1 look like? Well, actually it should be the B and C. It's usually off to this side. I guess you could do it this way where it was E and F, but most of the ones I've seen, BC is the one that makes it a 1. This is a 2, so it'd be A, B, G, E, and D. So we got A, oh, I'm sorry. Which one was this? 0, 1, 2. We got A and B are lit up, and then D, and then E and G, and that should light them up. So that's just a little 7-segment decoder. Okay, and then this are a list of the VHDL operators, and we're pretty much done with that one. The one I really want to get into is the next one, because I'm trying to get to the point where we're ready to go into our next project. And here we're using flip-flops and counters. And again, we're probably not going to actually do a flip-flop in this method, but this is going to help us learn a little bit that'll take us to the next level in doing the state machines that are coming up. Okay, so hopefully now this is probably done on an old version of 7. It should look all the same, and that means that Model Sim, it should look the same as iSim, but there may be something in here that looks a little different just because of that. Don't let it worry you. It can, if you do things the way we have been so far, it should be just fine. Okay, there's 3 methods to explicitly insert these into your design. You can instantiate a flip-flop. You can use the schematic capture tools and put it in there, or you can do it inside of VHDL using its description. You can use a process, and or registers can be inserted. So there's a couple of different ways of putting a flip-flop in there. Normally, you don't worry about that. You let VHDL, you let Xilinx figure that out for you. Okay, now here we go. Here's the logic for a D latch. And what I meant by a latch is it's a level triggered D latch. So we're saying when the clock input is high, so it's a positive level D latch. And this should look a lot like things that we already did in the last set of slides. When we got our inputs as our process sensitivity list, and then we started, if either one of these change, well, we're hoping it's probably going to be a clock or D because it's a positive level triggered. So if the clock equals 1, then let Q be assigned D. And this won't run again until one of those 2 changes. Well, that's good luck for us in this case, because if D changes, if we only put clock in there, this would only happen on the positive edge of the clock. And then it wouldn't run this process again, not until the clock changed. And in that case, it would look at any edge of the clock, which is unusual. But here we're saying also if D changes, so we're allowing the output to change either on the clock or on D. Okay. Okay, and the other thing that I think is kind of important here, nothing is stated about what's to be done if Q, or with Q, if the clock signal is low. It doesn't say anything. But what VHDL does, it implies that Q doesn't change. So you don't have to go in there and say, if clock is equal to 0, then Q is equal to, well, how would you put not change? It would be difficult to put that in there. So it's lucky for us that that's the way that Xilinx and VHDL works. If you don't have to explicitly state it, it just stays in its last state if we don't say something about it. Okay. Now, let's do as an edge triggered. Here, this is kind of a weird looking statement. Now we're not looking at D. So our sensitivity list is just the clock. We don't care if D changes. It's not important anymore. But our for the edge trigger, this is a way to do it. We've got clock, and then a single parenthesis, or sorry, a single quote, event. That's all like one key word in Xilinx. So those two, and the clock is one. So it's a clock event. The clock is changing. And the new value is going to be one. That tells me it's the rising edge of the clock. Now, somewhere in VHDL, you can look in those manuals, but do a search. I wouldn't try to flip through 200 or 300 pages of manual. But there's also one called a falling edge and one called a rising edge. And you can find those and use rising edge or falling edge on the clock instead of this. And it works the same way. So if you want to be different, some of you like to be different, so you could use that. But this says only change D or only change Q to equal in D when we have a positive edge of the clock. And other than that, don't do anything. So the process is activated by the clock. It only changes Q. Okay, so this tells us the process is activated by a change on the clock. And this is ensuring that only when it's a positive edge that it does something to Q. Other than that, Q will stay the same. Okay. Trying to see if any of that's. I'm sure you can go back and read any of this. I don't see anything in there that is so weird that I got to explain it. Okay, if we were going to change this to a negative edge trigger D flip-flop, what do you think you would do?
Clock equals 0?
When the clock is equal to 0. And when we do that, then that's what we got. So we still got a clock event. It's changing, but it's when it goes to 0. And when I synthesized it and looked at it, this is what I got. This is pretty weird. Now remember the other day when you were doing your third project with the flip-flops, could we find, we couldn't find a D flip-flop that had a negative edge clock, could we? Do you remember? This one has one. So it has all the stuff we normally have. We have an input buffer. D's connected to that input buffer, and then the output of the buffer goes to the D input of the flip-flop. Q goes to the output buffer, goes to the Q on the output. This is real strange here. This we're used to seeing, negative edge of the clock, but here it's even emphasizing that by saying that the clock signal is changing from 1 to 0 here. So it's an interesting way that it does it. Okay, here we've got, it's a little different. It does the same thing, but we're doing wait until. Okay, the good thing about the process or the wait until is when you start putting in some of these sensitivity lists, you'll end up getting errors on them, and you'll be going, what's going on? Which one's the error? And you start trying to take them out and put them in one by one to figure out which one's causing your error. And it sometimes just gets hard to find the one in the process or the sensitivity list that's giving you the error. You can do away with that sensitivity list by using wait until. So when we do that, we say wait until there's a clock event and the clock equals 0. So this is saying wait until there's a negative edge of the clock, and then make Q equal to D. Oh, let's see. Okay, that's kind of, I have to go back and mess around with that and see what exactly that means. I can't remember. Okay, so here we got uh, flip-flops and counters. Some are synchronous, some are asynchronous. We've seen those before. I hope you've seen synchronous and asynchronous clocks before. But which one down here? I've got a reset N. The reason it's a reset N is because the book I was looking at the time I was coming up with these, I didn't know Xilinx either, or VHDL. So the book I was looking at for examples used reset N. So I used the same one. It says that reset N is in the process list. So is clock. We're not putting D in here. And then here we're using a wait until, so we don't have to have a sensitivity list. But the important thing here is which one is a synchronous reset and which one is an asynchronous reset. You do kind of want to know that because it may become real important in a circuit that you're designing to have one or the other. So which one do you think is synchronous? Hmm? You're doing this. To me, that's this way. Which one is synchronous? The one on the left? This one. The one on the right. I'm not going to implement myself here. Synchronous. It is. Because here we're waiting until something happens at the clock. Then we're looking at reset. Here, we're going ahead and looking at reset, and then we're looking at the clock. Okay? So that makes it asynchronous. So this one, anytime that reset N changes, we can get here and say if reset N is equal to 0, then make Q equal to 0. It does not execute this part at all. It just clears out the output.
So if there's no reset in, then it's synchronous?
I'm sorry?
If you don't have a reset in, then it's synchronous, right?
If you don't have a reset, well, here we have it, but now it has to be synchronous with the clock. Okay? So here, D may be trying to say make it a 1, the output a 1, but our reset input is telling us make it a 0. So that really changes the behavior of this one. This one just clears it whenever we need it to clear it. Okay, so here's the synchronous D flip-flop. So it looks a little bit different. Here's reset. Okay, and here's for the synchronous. Is that really for the synchronous? I would have to run it again to check and make sure that was right. Here's a 4-bit up counter. Now we've got some signals that are coming into play here. We've got the signals count. What's important here on these signals is they are not input, or they're not. You can't get to them from the outside of the entity. They're all inside the entity. So if it were a chip, I would say it doesn't have an input or an output pin, so you can't touch these signals. Okay, so here we're saying we've got a signal that's called count, and it's not up here at all. sensitivity list is clock and reset. So if we mess around with either of those, then it's going to change things. It reset equals 0, then count goes to 0. That says that this is um, an asynchronous reset, because here is our clock event. And then it says if it's enabled, then increase the count by 1, else just leave count the same. Okay, now here we got count, and here I've got count all capitals. I don't think it mattered at all. Okay, and then you got to be real careful on which if and else and end if goes with which one, and that's why I've got them indented in the way that they are. And then down here I say Q equals count. So I'm not changing it, trying to change Q in here, and I believe you'd get an error if you did. And this starts to show why these are circuit descriptions instead of programs. Here I'm changing clock. Oh, I'm sorry. I'm changing count, but I can't change Q. And so I have to have count as a signal. And the reason is, if you were to do this and just use Q here, okay, and try to say right here, Q is assigned Q plus 1, or here, Q is assigned Q. You're trying to say that this output is equal to this input, but it's an output, right? So, and you can't say this output should be assigned this output. It's an output. So what would most of you do? Go, well, it's giving me this error about this thing being both an input and an output. I'll make it an in out and see if that works. But the true way to handle it is making it a signal. A signal, does it say anything about being an input or an output there? Doesn't. So it doesn't matter. It can be an input or an output. So signal, we can change that. And that's why inside this process, I'm saying that count, not Q, not the output of this thing, but Q or count is equal to 0, or count is equal to count plus 1, or count remains the same. And then when I get out of this process, I let Q equal count. Okay, and anything else is not going to work for you. Okay, and this goes into some of the explanation of that. So when you go back and read it, if you had to, this one is the code. It says the code for the 4-bit counter shown in the previous slide should produce one of the two circuits, depending on whether the synthesizer chooses D's or if it chooses D's. So it's going to do one of these. Again, I don't care. I don't care as long as I have it behaving in this way. So here I'm not being particular at all about make sure this is a T or make sure this is a D or make it a JK. I'm just saying I want this circuit to behave in this manner. Okay. All right. This one I decided to try in Xilinx to see, make sure everything happened correctly. I'm trying to think if there was an error in here somewhere.
Says it was.
Huh?
It says there's several errors attempting to synthesize.
Okay, there were several errors. I was thinking that's why I did it this way, to see if I could find some errors. So what were the errors? Here was one error. I may use single quotes. They were supposed to be double. I should have told you what the error code was, because that probably had a lot to do with me. If it's more than one, if it's not a 0 or a 1, yeah. Then if it's not one thing, yeah. Okay. What else? There should have been other ones, but I guess that was the only one. So the only difference here is that I used the double quote, or had to put the double quote there. Then this is a circuit that came up before, and I double clicked it, and I got this.
Whoa.
Right. That doesn't look like that, right?
But does it work?
Well, it did. I think it did. These are D flip-flops with a positive clock, and it says it's got an clock enable on it. And then these circuits for the inputs, and it's showing a clock going from 1 to 0. So it's showing a negative edge clock. This one is kind of weird. And then it shows these bus taps. We've seen bus taps, right? And it goes to a bus, the 4-bit bus for the output. So this is all kind of strange. These were just the D flip-flops. It chose to use D. I don't remember saying anything about making it D or anything like that. I didn't. So it chose this.
What's inside the LUTs? The loops?
Okay, here, this LUT had that. Yeah, it's a little crazy. A little different than what I would have done. The second one did this. It's a little different. And the third one did this. So naturally, this is piquing my curiosity. I'm going, wait a minute, what the hell here? So I put in, and I can tell this is version 7 because I put in a test bench waveform to see what would happen. So look at my clock. It's changing all the time. Every is that 100 nanoseconds or 150 nanoseconds, something like that. I don't know. It's kind of hard to tell here.
I think it's 150.
Well, it's got to be something like that because here it's right on the fallen edge, and then here it's in the middle. Here it's in the middle. It's something weird. Okay, here is when I enabled it, and then here I decided to disable just to just turn it off for a little while and see what happens there, and then enable it again. And this was the only time I used the reset to see if it was really synchronous or not. Okay, my output normally just shows up like that, but that's kind of weird. It shows up like that, and it'll show you the time that it's each one of its values, and give it to you in a decimal or binary value. But typically, I want to see what the actual bits are. So I did this, and then I ran the thing, and see, this is what I was saying about the outputs. It was saying this is 0, this is 1, this is 2, 3, 4, 5, 6, 7, 8, 9, and then it went to A, and then B, and then C, and then it got disabled. So it stayed C that whole time. Then it started counting again, and it went to D, and then E, and then it was about to go to F, and then right here, so it went right with the reset line going low, it changed it back to 0. So, and then it counts all the way. Now, I like to see the numbers, so here they are, or I mean all the waveforms, so there they are. And either way, you can do it like this, or you can do it with those. The only problem here is sometimes those are so small that you can't really read what's going on there. Okay. Okay, our next topic is going to be the state machines, and that's That's a really important topic, and it's going to use some of the ideas that are here, but we're not going to be specifically using this or that. Let's see how much we got. 10 minutes. I would like to just take a minute or two to look at the very beginning of this, just to give you an idea about what's coming up. We can have a synchronous or an asynchronous that does not use some kind of a clock. We're probably going to mostly be using synchronous, so we're going to be using clocks in here. Now there's two kinds of basic state machines, and one is called a mealy and one is called a Moore. And here's the main difference between them. A Moore, and this FSM stands for finite state machine. It acquires its inputs from the registers only, the output of the registers. Do you know what I mean by output registers here, or with these registers? They're just the flip-flops in the circuit, okay? They're memory. So we're going to hear them referred to as memory, we're going to hear them referred to as flip-flops, and we're going to hear them referred to as registers. And the clock goes in there. And then the output from that goes to our output logic circuit. So it might have to be conditioned a little bit before we get out there. In other words, it might be a binary 3, but a binary 3 might not be the code we need to do whatever it is we're doing out here, like turning on a light or something like that. So we might have to condition that input. But notice the Q comes back. This output from the registers, or if this is the memory of the circuit, then the output of the circuit is fed back to the input of the circuit, and that's what makes it a state machine. Okay? Now, in a Moore, this blue line doesn't exist. You cannot connect this input line directly to the output. In a Mealy machine, or in a Moore machine, you cannot do that. In a Mealy machine, it does exist. So you can have the outputs directly connected to the output of the circuit, or the inputs directly connected to the output. I am not, probably not, in here going to specify I want this to be a Mealy or I want this to be a Moore. But just so you know, if you go to graduate school and you end up in electrical or computer engineering, you'll be taking another class that's a lot like this, and you guys will be the best in the class, okay? Because you've already seen this before, until it gets to this part. And then when it's like Mealy or Moore, then that'll be the only real stumbling block you run into. And the guy over there that teaches it just says, you know, he gets on to his students that he's known in undergraduate. He's like, come on, you guys, these are the ET guys, and they're doing better than you. And he tells me all the time, your guys do better. And I just laugh. It's like, I'm thinking, you know, I've told them this before, so they already know about all this. So we're going to pick up the design steps starting there on Monday. And we really need to, or not Monday, Tuesday. We really need to go through some of these so that you can do your next, what do you call it, project, maybe even lab, I don't know. All right, any questions before I turn you loose? Because I got a feeling when I turn you loose today, it's like the door's going to get jammed. Everybody's going to get out of here at once. No more questions? Okay. I could say just go and see what happens, or make you go out row by row.
First row, you can leave.
First row can leave. Okay, second row can leave. Okay, and got a whole hour and 5 minutes